Hey guys, today we are going to be sort of rationalizing the delta H's, the general delta H's for this process of oil, and I'm just going to get straight into it in the heat of solution. So, I'm going to use Zumdahl's example, and I'm just going to rationalize it in a little further than they do. So let's consider a specific case of oil. We know that oil is not soluble in water, right? Here's my oil, hypothetically. These are not drawn to be accurate, and here's my water. And we can explain this immiscibility of oil and water, and by immiscibility I mean their disability to not form this homogeneous mixture, right? Because you will be able to evidently see the oil and the water when you mix them. When we consider the energy terms involved. So, what do I mean by this? Well, oil is a mixture of nonpolar molecules, right? That they're interacting through their London dispersion forces, which vary with size. So the larger the molecule, the more London dispersion forces. So for a typical nonpolar solute, we expect the delta H1 for this one to be relatively small, but it will be typically larger for large oil molecules because there's more dispersion forces, London dispersion forces to overcome. And again, likewise to delta H1, your delta H3 will also be small because the interactions of the nonpolar solute molecules and the polar wall molecules will be negligible because they're not sort of forming this compound and making a homogeneous mixture, as we said, their immiscibility. But their delta H2, which is right here, will be large and positive because these polar water molecules take a considerable significant amount of energy to overcome the H bonds among the water molecules to expand the solvent. So typically, let's say they're asking a mixture of oil and water, and the solvent is water, you'll see a significant energy difference in the water, so the delta H, let's say 2, versus the oil, because it doesn't have as much energy and it doesn't have as much strength. So, concluding that our delta H of solution, which is the sum of this, plus this, will be large and positive because of these two terms. And then since a large amount of energy would have to be expanded from an oil-water solution, this process does not occur to any appreciable extent, which means it's not necessarily favorable. So, and these same standards and arguments are gonna hold true for any nonpolar solute with a polar solvent. So a combination of something with water that's a nonpolar solute. The combination of a nonpolar solute and a highly polar solvent is not expected to produce a solution because they're not mixing correctly. And as we can see here, they're not gonna form a solution that is homogeneous. So that is the total idea here.